All right. So welcome to the day. It's going to be a fabulous day. I've got my Spider-Man on today. Oh, it looks like my Spider-Man is on upside down. There we go. Today we are going to be talking about our star. Reminder, your exam is going to be Wednesday. Today we're going to be wrapping up talking about stars, and we're going to talk about our closest star and how it's not always the best. Sometimes it has a darker side. And so that's why today's lesson is the dark side of the sun. So we talked a lot about, the beginning of stars, how stars evolve. We've talked about how stars create elements inside of them and also energy and heat. We are now going to be talking about how stars can affect us in a bad way.
Good morning. This is Coach Kelly. Just to make a short announcement, if you are interested in going out for basketball this year, there will be an informational meeting in the Commons tomorrow, right after school. Thank you.
And I think he means boys basketball because the girls basketball already had an informational meeting. But if you're interested in girls basketball, let me know and I can get you in touch with some people that will help you with that. So our question is a reminder from what we did last week because we have been away from each other for a week. And it says, will the closest star to the Earth ever supernova? Why or why not? So let's break this down. Jalen, first tell me, what is the closest star to our Earth? Okay, so we're going to start there. I'm going to write incomplete sentences. Come on, pen. The closest star to the Earth. Whoops. And we disconnected. Sorry about that, boys and girls. So the closest star to the Earth, there it goes. Here we go. To the Earth is our sun. The closest star to the Earth is our sun. Fabulous. This is what size star? Jalen, is it? Yes. This is a medium mass star. Now, Jalen, will a medium mass star ever supernova? No. This star will never supernova. B/C meaning because why, Jalen? Right. It does not have enough mass. So let's go ahead and show what will happen. Right now it is a main sequence star. It'll spend about 90% of its life there. And then as it evolves, it will turn into a red giant. Then it will just kind of collapse down to a planetary nebula. What's left in the middle is a white dwarf. And then over a much longer period of time, it will cool off and become a black dwarf. Nice job. Cole, how's that feel? Pretty darn good, I'd say. Feel all ready for the exam? Yeah. It's going to be great. It really is. I'm done with it. I feel really good about it. Tomorrow, I'm developing a really fun game. I think we're going to be playing some bingo tomorrow in class. So you're going to have all your notes out in front of you, and we'll do like a bingo review game. It's going to be fun. Anybody ever played bingo? Do you know what bingo is? Okay, so bingo is like, you're going to have a whole bunch of things here, and then you're going to mark them off as you go. Yes, dear?
How long is it left for?
How long is it?
How long?
Not. At that point, okay, so imagine if you've had a fire and you've got those coals that are just kind of glowing, white hot sometimes. The fire's not going, but it's just glowing. That would be like a white dwarf. The next day you wake up and you know how like those coals that were glowing white are now just black? That's a black dwarf. Yeah, you could touch it. I guess. Yes, theoretically you could go ahead and touch that. Good question. All right, any other questions before we move on? Fan-flippin-tastic. If you will notice in front of you, you've got a piece of paper and it says the dark side of the sun. Now, you will need your computers because we are going to end our class with an ed puzzle, but we don't need our computers right now, so keep them close. You don't want to spend a lot of time bringing them up again, but it's good for right now. Look at the picture that you have up on the screen, and you also have this same picture on your sheet. Do you see the Earth? Can you find the Earth there? This tiny little thing right here. I will change the color that I have. So this tiny little thing right here is the Earth, and it says the Earth to scale. So this is the sun. The sun is here, and it is just huge. This is what's called a prominence. So notice that you've got these bands of energy that are coming up and then coming back down. What is happening is the sun has a magnetic field that as the sun rotates, just like the planet Earth rotates, those magnetic fields inside can get twisted, and sometimes they can pop up through the surface. And what you're seeing here is you are seeing photons of light riding the bands of magnetic field. And so the photons of light are moving up and then they are falling back down along those bands of field. That works really well, and it's no big deal unless one of these bands snaps and throws a whole bunch of charged particles out into outer space, which is still no big deal unless the Earth is in the middle or in the way of that. If the Earth is in the way of that and we get sent something called a solar storm, or even worse, a coronal mass ejection, meaning that there is an ejection of incredibly highly charged particles, a massive amount at once, that's bad news for our Earth. Now, our Earth also has a magnetic field that it protects itself with, and sometimes these charged particles, when they reach the Earth, they will just get deflected by the magnetic field. If there's a lot of them, they will then go down the North Pole or the South Pole of the Earth, and you can see those charged particles light up the sky. That's called the Northern Lights or the Aurora Borealis. Has anybody ever been lucky enough to experience that? Me either, but one of these days, that's on my bucket list. I want to go see the Northern Lights. All right, so let's go ahead and look at the dark side of the sun. At 100 times the diameter of Earth and more than 5,000 degrees Celsius at its surface, it is safe to say the sun is both really, really huge and really, really hot. But what else do we have to know about, what else do we know about the sun's basic anatomy or structure? Other than sending energy to Earth through visible light, how else could the sun affect us? Today, you're going to learn about the natural cycle of the sun and how this relates to solar weather that could potentially impact us on Earth. So what I'm going to do now is I'm going to move to a PowerPoint presentation. Oh, did everything shut down? No, there it is. That's not it. Here's my PowerPoint presentation. And we're going to follow along with this. You have got this information on your sheet. This used to be a lab that we would have you do, but unfortunately, because of the corona, we're not doing that anymore. So if you can please follow along, this is the second part of the second paragraph on your sheet. Get this turned down so we can see. It says sunspots in solar weather. Our sun is always too bright to view with the naked eye, but it's far from unchanging. It experiences cycles of what's called magnetic activity. These are areas of strong activity that show up as visible spots or sunspots on the sun's surface. Has anybody ever heard of sunspots before? Okay, sunspots on the sun's surface. And these spots are actually just a little bit cooler in the center, but super hot around the outside. The reason they're cooler in the center is because the photons of light are actually being blocked from coming up to the surface. Remember Fina the photon? She can't escape up through that because the field lines are all kind of coiled. Think about like when you get a brand new Slinky and it gets all twisted and you're like, oh, that's kind of what's happening to these field lines. All right. So the centuries-old technique of counting sunspots is still one of the simplest and most reliable ways to estimate the level of solar activity. This is Galileo Galilei, and he studied the sun through a telescope. And if you've ever been told don't look at the sun directly because it'll hurt your eyes, that's true. Well, Galileo studied the sun through a telescope. So he wasn't just looking at the sun, he was focusing and magnifying that sunlight into his eyes because he was keeping track of the different sunspots through many years of his life. And he ended up going blind because of it. A small number of sunspots signifies what's called a quiet sun, while many sunspots on the surface of the sun suggest high levels of activity and the potential for solar storms. Imagine each one of those sunspots breaking free, kind of like if you pop a pimple and that pus kind of flies out. That's so disgusting, Mrs. McGrain. But imagine all that charged particles from the sun kind of bursting forward. And if we are in the way, that's bad for us. So we keep our eye out on high sunspot activity that might mean potential danger for us on Earth. All right, so step one on the sheet of paper that you have in front of you, that I will now get in front of me, it says we're going to look at the images and we're going to categorize them into what you feel are low activity images and which ones are high activity groups. When we're done, then we'll go ahead and flip over and see how we did on it. All right, so here are your the pictures of the sun right now. And I want you on your little chart where it says high activity or low activity, you're just going to put an A or a B or a C or a D where you think this is a picture of the sun with a high amount of sunspots or low amount of sunspots. So I'm going to give you a minute to do that. I'm going to turn my timer over, and in 1 minute, then we'll go ahead and talk about that. Does everybody know what you're doing? Pick up your pencil, and you're going to put different letters on the data table for high activity and low activity. You're going to put different letters. 3 of them are high activity, 3 of them are low activity. You're also going to be putting some dates. If you look in here, it says we're going to put the date in there too. So leave some space because you need to put the date in that data table as well. All right, that's been 1 minute. So now what we're going to do is we are going to move forward. Okay, so now we're going to click each image around and we are going to turn it over to see the date on the back. Unfortunately, I can't let you touch these images, so we put them up on the board. Now you're going to write each date in the appropriate column that goes with each letter. All right, so let's go ahead and look at letter A first. Do we think this is high or low activity? Okay, it is high activity. Go ahead and write the date, July 19th, 2000. You don't have to write out the whole, you can just say 7/19, 00 if you want. These are your notes. So for B, what do we think? High or low? Okay. Write down March 18th, 2009. Next to letter B. What do you think for C? It's actually March 18th, 2009. It's exactly the same picture that you just looked at. So letter B and letter C are exactly the same. They would both go in the low activity. What do you think about letter D? July 19th, 2000, I would agree. That would also, I would say, be very high. That is the same image as letter A. It's the same day. How about that? Remember, these are pictures of the sun. These are all pictures of one star, our sun. What about letter E? High. That is a high level of sunspots. February 27th, 2014, this picture was taken. And then we have one more. What do you think about F? Yeah, that one is low. This picture was taken in March 20th, 2017 of the sun. So what weird thing did we recognize here? If we look at July 19th, 2000, what do we notice? There's two different images of the sun on the same day. And so my question to you is, here we go. I just gave these to you if you need to look at them. It says, notice the dates March 18th, 2009 and July 19th, 2000 appear twice on your chart. Compare these pictures that have the same date. Why do you think these images look different? So I'm going to go back so that you can look at those images. Why do you think that this and this, A and D, are the same day, but they look different, and B and C are the same day, but they look different? I'm going to give us just 1 minute on the clock to go ahead and think about that and reflect before we start calling out answers. Because I want everybody to think about it. Think about everything we've learned this year so far about light, about stars. All right, there's our minute. What do we think? What are some ideas about why possibly might letter A and letter D look differently? Easton, you had your hand up earlier. You still want to share?
No.
Okay. It's the same star. It's the same day. Why do the pictures look different? Easton, give it a shot.
Maybe like one of the picture, like one half of the sun and the other is the other half.
Good thought. It is not one's the one half and one's the other half. It is actually the same side of the sun, because if you look up here, you can kind of see the sunspots are right here. This group of sunspots is right here. You've got these sunspots that are right here, but these look different. So you've got some sunspots that look just a little bit kind of different, different in those different locations. Okay, Here we go. Here's a hint. What do we see here? What is this picture of? Oh my gosh, y'all, what is this picture of? The EMS, the electromagnetic spectrum. And we know that there are lots of different types of light. You've got radio light, microwave light, infrared, visible, X-ray, gamma. I am telling you that, be nice that there we go. If we look at letter A, that is a picture of the sun that is taken in visible light spectra. What do we notice different then about D? Is D taken with visible light spectra? I would say no, because it does not look the same. We can see when we are looking at letter D, we can still see the sunspots, but we're seeing different forms of energy. This is something like X-ray light. So it's taking the picture of the sun in a different form of electromagnetic spectrum. So look underneath on your paper where it says step 2, notice the dates are a little bit different. Why do you think these images look different? And I gave you a hint. Think about the different waves of EM spectrum. These two pictures are taken with different, or they're capturing different kinds of electromagnetic spectrum leaving the sun. You need to write that down now. Everybody has to have a writing utensil in their hand, and underneath step 2 on your piece of paper, they're taken using different forms of the electromagnetic spectrum. It just goes to show us there's a lot more than meets the eye. I guess they're like transformers. There's a lot more there than we can see with our eyes, and so we need to use technology that allows us to see our closest star, the sun, through different wavelengths of light. And when we do that, we can study things like sunspots much differently. All right, let's go ahead then and move on to the next question. It says step 3, look at the graph. Please pay close attention to both y-axes. What is this graph showing you? So when we're looking at this graph, what is it that we are seeing? Look at the x and the y-axes. What is on this graph? Let's just put your hands up and belt it out. What's one thing that you can see on this graph? Easton. It's showing us sunspots. I would write that down. This graph is showing us sunspots. Vicky. This graph is showing us satellites. Cooper. And this graph is showing us time through years. 3 things you'd want to write down. Look at the graph, pay close attention to both y-axis labels. What is this graph showing you? It's showing us number of sunspots. It's showing us number of satellites. And it's showing us an amount of years. Easton, please put away your phone. So underneath step 3, you should have 3 pieces of data that it is showing us. Amount of sunspots, amount of satellites, and number of years. So an amount of time. Let's then go ahead and break this down. Can somebody please tell me which line represents the satellites? Kaylee. The blue line is representing the satellites. That means that the dotted line is representing sunspots. Okay, fabulous. So then let's go ahead and see what is happening as we are moving through time. Remember, time is always moving in one direction. Back up. I don't want this. Can I go back? Fantastic. I just want to go back in time, please. Back in time. Okay, that's super great. It's really pretty, but I just want to go back. Let me go back to here, and then I will go back. Okay, now let's go ahead and use the pen. Fabulous. All right, so if we are looking at our pen, we are noticing, and I'll change the color maybe to yellow. What are we noticing that's happening with the satellites through time? What are we noticing that's happening with the satellites? Cooper, what is it that you're noticing? They're like fluctuating. We get lots of satellites that are, and then we have they go down again. And my pen has stopped working, so sorry about that. There we go. So the satellites go down, the satellites go up, the satellites go down, the satellites go up, the satellites go down. These satellites represent what's called low Earth orbit satellites. These satellites are dropping out of orbit. So here we have a high number of satellites that are dropping out of orbit. Here we have a low number of satellites that are dropping out of orbit. So what is the relationship between the number of satellites that come out of orbit and the number of sunspots? Well, I don't know. Let's go ahead and check out the number of sunspots. As time goes, we have a low number of sunspots, and then we get a high number of sunspots, a low number of sunspots, and a high number of sunspots. So what do we see as the relationship between sunspot activity and the amount of satellites that are dropping out of orbit? What are we noticing as the relationship? I'll give us 1 minute on the clock to be thinking about that, and then we will share out what we think. What's the relationship between the number of satellites that are dropping out of orbit and the amount of sunspot activity on the sun? A minute takes a long time. And again, this is low sunspot activity. This is high sunspot activity. And our 1 minute is up. Somebody share out, please. What are we noticing as the relationship? How are they connected? As sunspot, yep, go ahead. Flip that around. Yeah, the more sunspot activity on the sun, or as sunspot activity increases, more satellites drop out of orbit. We lose more satellites out of orbit when there's an increase in sunspot activity. So we lose, like in around the year 1990, it looks like we lost about 45 satellites as we had a high amount of sunspot activity. That is one way that sunspot activity can affect us on Earth. And we use those satellites for things like communication. So as we are losing satellites, our communication systems can go down. Now, if you are somebody that is an engineer and you work for like Boeing and you are developing satellite systems, you are probably understanding this information and knowing that about every 11 years, your satellite might drop out of orbit. So you're not going to be spending all this money to try to make a satellite that's going to last 20 years if you know that your satellite probably has to only make it about 11. And then your company is going to have to send another satellite into outer space. The reason that this occurs is because of something called drag. Who here understands what drag is? Have you ever heard the word drag? I'm going to draw you a picture. I'm going to attempt to draw it here so that my friends at home, you can see this as well. I'm going to draw a picture of the Earth. Here's the Earth. Is that showing up pretty well? It is. So here's the Earth. What has the Earth got surrounding it? Atmosphere. Good job. Yeah, we've got an atmosphere that's surrounding the Earth. So the atmosphere is a very thin layer or a little envelope of gases that protects us. It's super, super thin. And our satellites are at the outer edge of that. I'm going to make these our satellites. Now, when we have an increase, can't really see that very well, sorry about that. When we have an increase in sunspot activity, it actually is a warmer period of time on the sun. So the sun is actually sending out a little bit more energy towards us. And when things heat up, what happens to their size? They expand. Like if you've ever toasted a marshmallow over the fire, that marshmallow will get larger in size. Well, the same thing happens to our atmosphere. When the sun heats up our atmosphere, it swells a little bit. So now our atmosphere gets just a little bit bigger, and our satellites start to drag in the atmosphere. And without that drag, those satellites are doing really well, and they're moving along, orbiting around the Earth. But when the atmosphere gets a little bit bigger, it'd be like if I said, Owen, run as fast as you can across the yard. Owen would be able to go a certain speed. If I said, okay, now Owen, run, and he's going to be running really fast, and then all of a sudden he's going to run through water, knee deep, right, up to his knees. What's going to happen to his speed? He's going to slow down. He's going to experience drag. Okay, so what's happening is if these satellites then start dragging themselves through the atmosphere, they start to slow down, and then they begin to spiral in, and they will crash on the surface of the sun. That happens in about 11-year cycles. You need to write that somewhere on your paper. 11-year cycles. Probably under what is the relationship between the number of satellites that come out of orbit and number of sunspots. Okay. Worked really well, actually. I really like this drawing feature. Erase it really quick while you're writing. Maybe if I could get them all at the same time, but that's okay. There, that's not bad. All righty. So this is what I want to show you about an 11-year cycle of sunspot activity. We can see that in 1996, we have low sunspot activity. 97, 98, 99, 2000, we can see that the sunspot activity is increasing, and then it starts to decrease over time, and it's back and resets itself. And so this is pretty consistent. Every 11 years, give or take a few years, we get high solar activity, low solar activity. And you better believe that our scientists are watching this, because there is something called coronal mass ejection or major solar storms that can be sent to us that can be quite devastating. All right, let's go ahead and look at what our sun looks like today. If you flip over your paper, please. I'm going to bring up the sun today. This is our Solar Dynamics Observatory. It is a very special satellite that was put into outer space called SODO. And this is what our sun looks like right now. Stick with me. I see some of you are sleeping. So I want you to look at this, and I want you to tell me, based on what you see, do you think that the sun is experiencing low solar activity or high solar activity today? And this is today. I'll show you the date. So if you notice, this is 9/11/2020. This is what it looks like today. Please write that down, high or low. Here's another picture of it in a different light form. There's another picture. You can see really those bands of magnetic fields that have become twisted, and the energy is just kind of riding up on those bands and then going back down. And when that happens, this is what it looks like on the sun. So this is what the sunspot would have looked like to Galileo through his telescope. He never would have been able to imagine this is what the sunspot looks like through a different form of electromagnetic radiation. All right, so now that you have your ideas down, and again, this is your observations, not my observations. What I want us to do is I want us to look at this next portion, and this is about coronal mass ejections. It says, watch the coronal mass ejection video on Edpuzzle. I am right here now. Watch the coronal mass ejection video on Edpuzzle. And then what you're going to do is when it stops and asks you a question, you're going to write down the answers on your piece of paper. You are not going to put the answers in Edpuzzle. You're going to put the answers right here on this piece of paper. Does anybody have any questions? So what do you need to have out in front of you? Computer and your paper. That's right. Computer and your paper. So we are right on this particular area right here. Okay, so you're going to go to Edpuzzle, and when you get to Edpuzzle, let me see if I can get you to Edpuzzle. When you get to Edpuzzle, you have to please make sure that you're in the correct classroom. You should be in ESS 2020 period 3, since this is period 3. Obviously, at home, if you are watching this, you need to be in your specific class period. Now, if you have anything else like Migraine, Earth, and Space, get rid of it, delete it. You want to add a new class or join a class, making sure that you are in the correct class. Where do you find those codes? Well, those codes were on last week. I will go to our main Canvas page, click on last week, and I will bring up those codes for you. Those codes are located right here. So period 3, you have KEFFRIZ. That is your code. All of your codes are right here. You're going to join a class. Easton, do you not have your computer? Dang it, man. Slacker. Do me a favor and cover your nose, bud. All right, so that is going to bring you to the end of class. So, Easton, you need to find something else to work on, please. Do you have your phone that you could maybe get on Edpuzzle?
Yeah.
Give it a try. For those of you at home, I am now going to end the screencast. If you have any questions, please make sure you email me, and I miss you dearly.